G'day, mate. Welcome to my presentation on predicting rain in Australia. And I promise that will be the first and last time I slaughter Australian lingo. Weather has an immense impact on our lives. From our food supply to our mood, it has the potential to influence every aspect of our well-being. People have always been interested in trying to predict the weather. Some of the earliest attempts at weather forecasting date back to 650 BC, when the ancient Babylonians attempted to predict short-term weather changes using optical phenomena such as halos and clouds. Aristotle's famous Meteorological, written around 350 BC, was considered an authority on weather for almost 2,000 years. The end of the Renaissance gave birth to specialized weather instruments, such as the thermometer and barometer. But weather science really began to rapidly develop once the telegraph enabled routine transmission of weather observations from an observer to a compiler. Furthermore, weather balloons facilitated the gathering of atmospheric data, and advances in computers allowed the mere possibility of real-time numerical weather prediction to turn into an absolute reality. By 2007, in just the United States alone, over 210 million weather observations were processed daily, with a computational speed of 14 trillion calculations per second. The complexity of modern numerical weather prediction is astounding, and it continues to grow. But what if there was a simpler way? What if we could predict weather phenomena, such as next-day rain, from just a few local observations? The idea of using machine learning to predict the weather is very attractive. Combining neural networks with traditional numerical weather prediction has been shown to improve computational speed without sacrificing accuracy. Holstrom, Liu, and Vo applied both linear regression and functional regression models to predict maximum and minimum temperatures. And while their models did not perform as well as traditional forecasting in the short term, the models did show the potential to be more accurate in long-range forecasts. Weather forecasts are inherently uncertain. Currently, the only way to measure uncertainty in weather forecasts is to compare various numerical weather simulations, which is computationally expensive. Machine learning could be the solution to measuring uncertainty. However, the downside is the vast number of past forecasts needed to train an accurate model. This project focuses on four main questions. Which variables have a significant relationship with rain tomorrow? Which variables are more important in predicting rain tomorrow? Which class of model, from logistic regression, random forest, or gradient boosting machines, does the best job of predicting rain tomorrow while remaining practical, with an emphasis on the practicality of the model? And finally, does feature engineering improve the accuracy of the model? The data is downloaded from Kaggle. It consists of 145,460 observations of 10 years of weather data from multiple locations. It has 23 different variables. All of the variables either read in initially as character variables, which are listed in blue, or numeric variables, which are listed in red. Our target variable is rain tomorrow. It is coded as yes if precipitation the next day exceeds 1 millimeter. Otherwise, it is coded as no. As shown here, the target variable is imbalanced. There are 31,877 yes outcomes compared to 110,316 no outcomes. Approximately 22% of the data has a yes result. This is right on the boundary between a mild imbalance and a moderate imbalance, which means that the imbalance can likely be mitigated by simply carefully choosing a more appropriate evaluation metric, such as using balanced accuracy, the trade-off between specificity and sensitivity, instead of using true accuracy. As you can see, the data set also has quite a few missing values in the target variable. There are 3,267 nulls in our target variable. But the target variable is not the only variable that has missing values. All variables, except for location and date, have at least 1,000 missing values. Simply dropping observation with nulls from the dataset decreases the dataset from 145,460 observations to 56,420 observations. These variables listed in red are missing values for over 1/3 of their observations. In fact, almost half of the observations are missing in the sunshine variable. Because one goal was to develop a practical model, these variables are not usable. How can we predict rain for the next day if the model requires a value that is recorded only 2/3 of the time? The situation becomes even more dire when we start looking at the data by location. As you can see, there are variables that do not have even one record for one or more locations. For example, Albany does not have a single record for wind gust speed nor for wind gust direction. And Newcastle only recorded those values once. This essentially expands our list of unusable variables to all of the variables listed in yellow and red on this list. Another issue with the data is that many of the variables are strongly correlated. All the temperature variables are positively correlated, and sunshine and clouds are negatively correlated. Both random forest and gradient boosting machines are more robust to issues with multicollinearity, but this will heavily impact the logistic regression model. Here are the distributions of the unusable continuous variables. It's a shame we can't use these variables because some of them have very visibly different medians. Here are the distributions of the usable continuous variables. Again, we can see a few variables with visibly different medians. As for the categorical variables, there does appear to be a difference between the most common wind direction at 3 p.m. When we look at the mode of the outcome of no rain tomorrow, we see that the most common wind direction is from the southeast, whereas compared to the yes outcome, the most common direction is west. However, this variable changes significantly when you look at individual locations. For example, if we switch and just look at Catherine, now we can see the predominant wind directions being east-southeast for no rain and west-northwest for rain. This same pattern occurs when we look at wind direction at 9 a.m. Although when we look at all locations, it looks like the mode is the same from north compared to north. When we start to look at individual locations, we can start to see differences. For example, Catherine, again, has the most common wind direction coming from the southeast when there is no rain the next day, and the most common wind direction coming from the west-northwest when there is rain. When looking at the average daily rainfall and maximum and minimum temperatures by month, we see the expected trend in temperatures, with both the maximum daily temperature and the minimum daily temperature at their lowest in the middle of the Australian winter. Average daily rainfall does not appear to have any visible trends. It seems to go both up and down at random. However, when we look at specific locations, trends do start to appear. For example, Perth receives higher amounts of rainfall during the winter, and when we compare that to Alice Springs, their winter, they receive the lowest amounts of rainfall, with their peak occurring in the middle of the summer. The data was cleaned and processed in the following ways. The date variable was removed. All character variables were converted to factors. The unusable variables, in which one or more locations had no records, were omitted. Because max temp and temp at 3 p.m. are so highly correlated, and min-temp and temp nan were so highly correlated, missing values for each variable were imputed by using the difference of the means between the two variables in each pair. All remaining observations that had null values were removed. In addition to removing variables, two new features were created. Temp change, the change in temperature from 9 a.m. to 3 p.m., and hum change, the change in humidity from 9 a.m. to 3 p.m. Temp 9 a.m. and temp 3 p.m. were chosen instead of max and min temp to be more consistent with humidity. Inferential statistics, specifically the significance of variables, were tested using an alpha cutoff of 0.05. The significance of categorical variables was tested using a chi-square test, and the significance of numerical variables was tested using single predictor logistic regression. For both tests, the null hypothesis was that no relationship exists between the two variables, and the alternative hypothesis was that there is a relationship between the two variables. Three different classes of predictive models were built. The first model was logistic regression. The strengths of logistic regression are that it is computationally fast and enjoys high interpretability. However, it also has many underlying assumptions. One assumption is the absence of multicollinearity. Variance inflation factors were calculated and correlated variables removed from the model. Another assumption is linearity in the logic for continuous variables. This assumption was checked using diagnostic plots. Linear regression can also be affected by imbalanced data. So the trade-off between sensitivity and specificity was used as an evaluation metric, as well as looking at the ROC curve and area under the curve. In building logistic regression models, two separate data sets were used. The first data set has all the original usable variables, and the second data set used the two newly created features in place of all the temperature and humidity variables. Each data set was split into trained test sets of 70% and 30% respectively. Variance inflation factors were used to remove variables with multicollinearity issues. Backwards selection was then used to find the best model for each set. Hosmer-Lesmanshow goodness of fit tests were run to verify the adequacy of the models. The best performing model was chosen using balanced accuracy as the evaluation metric. Once the best model was selected, the sensitivity-specificity trade-off was used to find the optimal threshold for classification. Random forest models were also run. One of the strengths of random forest is that it uses bagging, which can mitigate issues with imbalanced data and missing data. Another strength is that variables for each tree are chosen randomly, which mitigates the issue of multicollinearity. Random forest models are also less impacted by noise or outliers compared to logistic regression models. However, random forests take a much longer time to run. They are more flexible and complicated, which results in lower interpretability, which is essentially limited to partial dependence plots. Also, random forest models cannot predict beyond the range of the training data. This last weakness was not an issue for this project because it used classification instead of regression. For the random forest models, three data sets were used. A data set containing the original usable variables, the data set using the new features, and then a data set strictly for comparison that used all original variables but omitted all of the null values, leaving only 56,420 observations. Like logistic regression, the data sets were split into 70-30 trained test sets, and balanced accuracy was used as the evaluation metric. Finally, an expanded grid was utilized to tune the hyperparameters on the best model. The third class of model was a gradient boosting machine. Like random forests, the strength of gradient boosting machines are that they use bagging and can do well with imbalanced data. Unlike random forests, gradient boosting machines can also use boosting. They build trees sequentially so that each tree tries to improve upon the previous one. Gradient boosting machines are more complicated and can have a very long runtime. The two models for this project each took nearly 7 hours to run. They have low interpretability and are prone to overfitting. It can also be very difficult to tune the hyperparameters of the model. For the gradient boosting machines, I used the same data sets as logistic regression. one with the original usable variables and one with the new features. Again, they were split into training and testing sets using a 70-30 split, and balanced accuracy was used as the evaluation metric. The caret package was used to tune hyperparameters, and caret was used to scale and center the data. For the inferential tests, chi-squared tests were used for categorical variables, and single predictor logistic regression were used for numerical variables. The date variable was not tested. All other variables were significant with a p-value of less than 2 × 10⁻⁻16, even variables that were omitted from the predictive models. For logistic regression, the Hosmer-Lemeshow goodness of fit test determined all models to be adequate. The best balanced accuracy was the model using the original variables. However, the diagnostic plots were slightly better for the engineered features model. Here is the ROC curve and optimal threshold for the best model. The area under the curve is 0.839, revealing a fairly decent model. The optimized threshold was 0.22. So any prediction with a probability of 0.22 or higher was predicted to have rain tomorrow. The balanced accuracy for this optimized model was 76.07%. Here are the exponentials of the coefficients for the model. As you can see, most variables have a small impact on the odds of rain tomorrow, as most values are very close to 1. However, wind direction at 3 p.m. from the north-northwest and from the northwest are 3 times as likely to have rain tomorrow as compared to the base direction from the east. The best model for random forest was also the model using the original features and had a balanced accuracy of 73.35%. The most important variables identified were humidity at 3 p.m., location, and wind direction at 3 p.m. When comparing the practical model with a random forest model using all of the original variables, the unusable variables of sunshine, pressure at 3 p.m., and wind gust speed and direction also become the most important variables. For the 2 gradient boosting machine models, the balanced accuracies were very similar, with 72.03% for the model with the original usable variables and 71.93% for the model with created variables. In conclusion, as shown in the previous slides, all variables had a significant relationship with rain tomorrow. The variables most important for prediction were humidity at 3 p.m., location, and wind direction at 3 p.m. The model with the best overall balanced accuracy was the optimized logistic regression model using the original usable variables. In all 3 model classes, the newly created features did not improve the accuracy of the model. Comparing the 3 practical models to the model using all the variables revealed that there could be a benefit to the inclusion of all variables. The balanced accuracy of all variables was 3% higher as compared to the practical model for random forest using only the usable variables. Because of this, I strongly recommend to encourage all weather stations to consistently keep data on all variables so that they could be used in a practical model. I also recommend trying a neural network or spending more time to more carefully tune the gradient boosting machine. Another thing to try would be to do more engineering options, such as comparing a change in more of the variables or utilizing aspects of time series data and tracking short-term trends and lags. Finally, the creation of multiple models tailored to specific regions could be beneficial and increase accuracy. Thank you so much for your time in reviewing this presentation. These slides can be found on Tableau Public, and the R code can be found on GitHub. My username for both sites is Marla Seth.